Good afternoon. So in the last class, we began looking at basic ideas of Kolmogorov phenomenology and seeing how initially it gives us an idea of the range of scales in turbulence, which is one of its typical features, right? That the turbulent flow is multi-scale and it has features from the large scale at which you are forcing through a whole range of scales down to the scale eventually where viscosity becomes important. And so it's multi-scale, apart from the fact that it is fluctuating in time and chaotic. And this is, of course, we are doing this thing so that we have the basic information we need to model turbulence as a stochastic phenomenon, right? Or to replace it with a stochastic field and then to look at implications for mass transport and other transport processes. So carrying on in that theme, right, there are a few more things that warrant discussion. So just by way of recap, what we saw is if we're looking at homogeneous isotropic turbulence, right, far away from walls, right, with no strong mean shear or mean flow. So in such a situation, if you're forcing the flow at some large scale L, right, and you are inputting energy at a fixed rate, the flow reaches a stationary state. And what you want to know is what is the nature of the range of scales, how does the velocity field scale, etc. So we said we are inputting energy at some rate epsilon. This is the rate of energy input per unit mass, right, per unit time, in a fluid of kinematic viscosity nu. Okay, so those were the inputs. Okay, and the nature of the large scale forcing was such that it was happening at some scale capital L. Okay, then you have a range of scales inside the flow. Okay, so you have the large scale, capital L and capital U. So L is the large scale, right? Its corresponding velocity is capital U, which can be obtained from the epsilon. Okay, because U cube by L must be equal to epsilon. And correspondingly from L by U, you will get the time scale capital T. Okay, so I'm just defining these as the large scales. You have to fix one of them, then you will get the other from epsilon. Okay, then we have the inertial range of scales, right, which are below the large scales, but much above the dissipation range where viscosity is not important. Right, so in the inertial range, we have U at scale L must behave like epsilon L to the 1 by 3, right? Or this U cube by L will go like epsilon. And of course, that carries all the way to the large scales. So in the large scales, we also have, right? And the same is true here. Okay, but that gives us the inertial range scaling for the velocity. So this just means that if I'm at some distance, small subscript L, right, the typical velocity difference I will see will go like that L to the 1/3. Okay? So you think of it like there is an eddy of some size. The velocity of this eddy, right, which is going up somewhere, going down somewhere, that will have a typical magnitude which goes like L to the 1 by 3 as I look at smaller and smaller eddies. And there is this whole hierarchy of eddies. Okay? This is the cascade picture that we discussed in the last class. So this carries all the way until I hit the Kolmogorov scale, which is the start at which I see dissipation. So then you have the Kolmogorov scale, right, which marks the onset of dissipation, right, and that length scale eta we calculated, right, in terms of nu and epsilon. Right, and corresponding to that, there is of course a tau eta, right. And those things also you can calculate as we did in the last class. So the important thing is this sets the length scale at which I first start seeing the effects of dissipation. Right? At this scale, the effective Reynolds number, scale dependent Reynolds number is 1. We saw this in the last class. And below this, we get the dissipation range of scales, right, where the flow is smooth. So here we will see that UL goes like I mean, the velocity gradient is constant, right? So we can estimate the gradient such that it has to dissipate that amount of viscosity, remembering that dissipation is nu times gradient square. So from there we directly get it goes like L epsilon by nu to the half, because epsilon should be u by L the whole square into nu. Correct? That is the relation we have. Right? Okay, so here this flow is smooth in the sense that the gradient velocity goes linearly with L, right? Or the gradient is something constant, right? Whereas these inertial range scales, it goes like L to the 1 by 3. So that's what I said, the flow is rough. Right? If I try to if I filter out the field and only keep these inertial ranges and I remove the dissipation, and if I try to calculate a derivative, you'll see it will blow up. Right? So if I am at a certain range, the flow will look like as if it has discontinuities. But if I zoom in, then I will see what looks like a sharp jump. If I zoom in sufficiently, eventually will become smooth. But I have to zoom in below the Kolmogorov length. Then I will see that, okay, actually the flow is smooth because of course there's viscosity. If I zoom out, the effect of viscosity is happening at such small scales that it will look like the flow is suddenly, there's a large velocity, suddenly it's going to zero. That's what I mean by it being rough. Right? Because if I try to calculate derivatives only looking at the filtered large scales, it will look like there are discontinuities and jumps. And that's why the turbulent flow looks so chaotic and rough in space. Okay, so this is the overall picture of how the flow field varies, how it is multi-scale. Okay. And I think in the last class, what we just showed is that, yes, you can have a scale-dependent Reynolds number, which will be much larger than 1 above the Kolmogorov scale, showing you that the viscosity is not important, and much smaller than 1 below the Kolmogorov scale, right? And at the Kolmogorov scale, it is 1. And this whole range of scales is almost necessitated by the fact that I'm pumping in energy only at the large scales, right? And I'm able to dissipate by viscosity only at much smaller scales. And somehow the energy has to get transported to the small scales. Right? So from that physical argument, and then by using just the fact that the energy transferred from scale to scale in the inertial range cannot depend on viscosity, only on that particular scale. If you hypothesize that, you get this behavior just from dimension analysis. Of course, there are lots of assumptions here, including the fact that this transport of energy across scales only depends on that local scale, right? Whereas in reality, there can be all kinds of interactions across scales. So all these things, of course, bring in to cause deviations from the Kolmogorov behavior. But at leading order, the Kolmogorov theory works quite well, in the sense that certain predictions that follow from Kolmogorov, at least at leading order, find good agreement with the experiment. Then, of course, there are subtle corrections. If you want to be very accurate, you have to correct for it, which has to do with facts that there are interactions among scales. There are so-called intermittency effects and so on, which we won't get into in this course. But to get an initial idea of things, it works remarkably well. Okay, so let us now see what are some of the implications of this kind of phenomenology, which can be tested in experiments, which in fact have been tested. Okay. So that's what we're going to do next. So the first of these is what's called a way to check this inertial range, right? There are two ways typically these are done. One is the structure factor and the other is the energy spectra. So let's look at them one by one. Okay, so what one does is you want to think of something I can actually do experimentally to check whether you have this sort of scaling behavior of the velocity, right, in this inertial range of scales. That means on length scales that are smaller than the large forcing scale, but bigger than the Kolmogorov scale. So the question is, how can I get scale-dependent information given some velocity field? Okay, I have some three-dimensional velocity field. You can, for example, do a particle image velocimetry and get the velocity everywhere at different points in space. How do I extract scale-dependent information? So one way, as I said, if you want to be a computationally heavy way of doing this would be to take this 3D field, assuming you have very accurate data, and then you can do a Fourier transform scale by scale. Right? So that will come in when I look at what's called the energy spectra. You can also do like a wavelet transform to get scale-dependent information. But a much simpler thing to do, particularly when you don't have such three-dimensional field data, is to calculate what's called a structure factor. So what you do is you take a velocity difference. So x is some position vector, okay? R is a difference vector such that I can calculate the following difference. Right? So you at any position x in space, okay, I look at u at x, and then I take a displacement vector r, and I calculate the velocity. So it's a velocity at 2 points, I take the difference, okay? And then I can average this quantity, right, for all different x positions and for different r vectors, okay, but keeping r constant. Okay. So then I will get a structure factor or a velocity difference that depends only on the magnitude of r. Okay, so when I vary r, I'm really varying only the orientation. So I should say varying the directionality of the r, not the magnitude. Okay, I'm keeping it at different magnitudes. But then I'm averaging it over space. So at any point in space, I can make a ball of size r and take the difference of velocities. I can do this all over space. So this will give me the equivalent of like an ensemble average. And because it's homogeneous and isotropic, I will get this to be only a function of r. Okay, so I'll remove this stuff here. You can interpret, you can just interpret it as an ensemble average. That means I have, remember, a field, then many realizations of the field. I take any point, I take any vector r, okay, and I do the ensemble average over many different fields. This will end up being only a function of the magnitude r. Why? Because the flow is homogeneous, that means statistics don't depend on position, and isotropic, that means statistics should not depend on direction. Okay. So because of that, you can calculate, instead of doing an ensemble and getting different realizations, in a given snapshot of the flow field, you simply do this calculation and average over x and over orientations, you will get the same object. Okay. So this is the structure factor, and the second order structure factor is when I take this squared. Okay, so I take the square of that difference and average. That's the second order structure factor. So I'll put a square. Then you can get third order, fourth order. Instead of taking square, you take the cube, take the fourth order. That gives me higher order moments of a distribution. Right? So if you like this delta u, you can get a PDF of it, right, for any given r. It will have a mean, a variance, and so on. And then the different moments are the different orders. Now, why we look at the second order is because it's like the variance of that distribution. Of course, the mean will be 0, but I have the magnitude, right? So without the magnitude, it would be 0. But the second order structure factor is like the variance of this difference. Okay? And that should connect with what I have here. And yeah, so now based on this scaling, right, in the inertial range, so for this r less than the large scale capital L, okay, but greater than eta, what I would expect based on this scaling, that the u difference goes like 1/3, I would expect the second order structure factor, right, to go like epsilon L to the 2/3 r, sorry. Okay. Okay, within the inertial range. If I go below, if I go smaller than eta, then the flow will become smooth and this delta u square will go like r square. Okay, but if I'm in this inertial range, I should see this behavior. Okay, r to the 2/3. And it's something easy to calculate, right? You can just keep two probes at a given separation and measure it in different places of the flow. You can get statistics, calculate the variance of that, and then you will see that it will go like r to the, which means you take two probes at some distance, then you keep changing the distances, and you plot this, right? And you will get a power law with 2/3. So what it tells me basically is that one way to get scale dependent information is to measure differences, so-called 2-point statistics, at different distances. That's just a simple way of probing the structure of the flow, right? And if the differences scale with r as I vary the distance r between the probes, right? If they go linearly, then I know the flow is smooth, right? Or if the squared goes like quadratically, then the flow is smooth. But here it doesn't, right? It has a smaller power than r squared, much smaller. It's r to the 2/3. Right? That tells me the flow is rough. Okay, so this is one thing I can calculate, which I can measure and has been measured in different flows, and you get reasonable agreement with this 2/3 behavior. Okay, another thing I can do is call the energy spectra. Okay, so the way you think about this is you take a 3D velocity field and you do its Fourier transform. Okay, and then you look at the amplitude of that Fourier transform in different wave numbers. Of course, that will give you the energy spectra because you know this Picard's identity, right? That the kinetic energy sum in physical space is the same as summing up all the Fourier mode amplitudes. So what I can do basically is write the total kinetic energy Okay, so the average kinetic energy of the flow can be written as the integral of So in principle, I'm saying that if I have a given flow, the mean kinetic energy of the flow can be decomposed into Fourier mode such that if I sum up this E of k is a spectra, right? It's, if you like, the energy content of different wave numbers. If I integrate over wave number space, I'll get the total energy. So you decompose the total energy in space among Fourier modes. Okay, the way I would actually do this is I would write the velocity field as so this is the in principle thing, right? Numerically, of course, I will have to discretize my field. Okay, so you can think of it in 2D. Of course, you can extend it to 3D, but let's think of it in 2D. If I have x and y, then I can do a Fourier transform kx, ky, and I will have different points, right, in the Cartesian grid. I can write my velocity field as summation Okay, so I write my velocity field in three-dimensional velocity field in x, y, z. I do a Fourier transform, okay, finite Fourier transform, and then I sum over all different kx, ky, kz, okay, such that I'm taking different combinations such that the amplitude k will go from 1 to some cutoff k max, okay, and of course I take k minus k so that I get a real number, right? So I add it with a complex conjugate, and this magnitude k is given, of course, by kx square plus ky square plus kz square. Okay, so if you want to think of it geometrically, when I take the field u and I do a Fourier decomposition in the wave number space kx, ky, kz, okay, so you imagine out of the plane, but for simplicity we can think of it in 2D. Each point here will be a certain wave number, okay, kx, ky combination, and if I'm looking at a particular wave number shell, right, so let's say k equal to 1, then I will be all the modes, right, in that shell. So this has many different discrete modes. I will sum up all of them to get a particular wave number magnitude k. And then, so if I am looking at large wavelength structures, I will look at a shell close to k equal to 0, and high wave number features will be in shells at much larger circles, right, in the k space. And I'm going to sum up all of that. So if I sum up the amplitude of all the modes in this particular shell, that is what is going to give me this E of k, suitably normalized. So in the end, this will be approximated by a summation, okay, delta ki. This delta ki typically you take to be 1. So I sum up k equal to 1, 2, 3, 4. So the delta ki is typically 1. Okay, this is usually 1. And this will be the energy content in that discrete shell. Okay, so anyway, this is the way I would do it numerically, but the upshot is that if I have a 2-dimensional or 3-dimensional, usually 3-dimensional turbulent velocity field, I simply take its Fourier transform. Okay, I will have the amplitude among different Fourier modes, and then I just take the square and sum up those amplitudes. Right? And if I suitably construct it using isotropy to rewrite it just in terms of the energy per unit shell, wave number shell, okay, then I will get this E of k. Now the question is, how should E of k behave again if I'm in the inertial range of scales? That's what we'll look at. Actually, I can do it here. Okay, so I know just from this relation, okay, that so I'm now looking for a scaling relation, right? How should E of k vary as a function of k? So I know that E of k dimensionally, right? So k times this E of k goes like u square, right? And that u square itself should go like this, right? L to the power 2 by 3. But L to the power 2 by 3 is itself 1 by k. So it's k to the minus 2 by 3. Okay, this is just to get this. I want to know how E of k should vary with k, okay, so that it's consistent with the inertial range scaling. So for that, I'm just saying dimensionally, this is E of k into a wave number, right? That should give me the energy in a particular shell. So k times E of k must behave like UL square, right? Not the total U, the kinetic energy of that particular shell corresponding to wave number. Relation between the length and k is, of course, L goes like 1 over k. The length scale is 1 over the wave number. So that's how I get this. So then I should get, finally, that will get k to the minus 2 by 3 minus 1, which is minus 5 by 3. Right? And this is called the Kolmogorov spectrum. Okay, so if this Kolmogorov phenomenology works so that you have this inertial range of scales, one way to verify it is you plot the structure factor as a function of r. Right? Again, you will see very large scales, it will do something, then it will hit a power law, which will show you this 2 by 3 behavior, then it will become steep, it will behave like r. Okay? So that, of course, will increase, the delta U will increase, okay, with r. But the energy spectra, the energy content in the mode decreases as you increase the wave number, because, of course, high wave numbers mean smaller lengths. So if you look at the energy spectra, typical plots, okay, you will have E of k versus k. Right? There will be some energy content in the large length scales. That this stuff depends on how you are forcing and so on. Then, regardless of the forcing, it will hit a power law, right? Which will be like this slope is k to the minus 5 by 3. And then it will cut off somewhere and become steep. It will cut off somewhere and become steep. And this typically happens at k eta, right, which goes like 1 over eta. So at a wave number corresponding to the inverse Kolmogorov length, this power law behavior will end and you will become steeper, because, of course, that is when you are hitting the smooth flow. Usually it has some kind of exponential decay form. Okay. If this doesn't decay, then there will be energy content sitting in smaller and smaller wave numbers. The flow will not become smooth. So at some point you will cut off because of viscous dissipation. But in this range, you have this k to the minus 5/3 behavior, which is the classic signature of 3D turbulence. So if you look at the lecture I pointed you to by Jeremy Beck on YouTube, he will show you experimental data from various experiments, okay, real experiments, which have tried to achieve more or less homogeneous isotropic, and there you get this minus 5/3. So usually you will see it far away from walls, as I had said, or in grid turbulence. But you get very good agreement, at least of the energy spectra. And this makes sense because this energy spectra, like the second order structure factor, is related to low order moments of the turbulent fluctuations, like the variance. Right? That's in fact the lowest order thing you can get because the mean is 0 in homogeneous isotropic. But if you look at higher order structure factors, so if you think of the velocity difference as a PDF, this gets the core, it's only the variance, right? If you look at 4th, 5th, 6th order, then you are sampling the tails. These are the extreme events of the turbulent flow. Those start to show deviations from Kolmogorov behavior. These are called intermittency corrections. He discusses some of that in that lecture. We won't go into it in this course. Okay? But at least at leading order, right, and you get very good behavior. So now if I want to cook up a field, a stochastic random field which mimics a turbulent flow, one of the basic things I'll want to do if I'm interested in spatial structures and spatial information is to put in this Kolmogorov spectra. So all that means is when I'm making my velocity field, I can create my velocity field using a sum of sines and cosines, right, or exponential Fourier modes. And then I just have to take care of what are the amplitudes of the different modes. So if I make the amplitude a function of k such that it obeys this behavior, right, that means the uk square by k, or rather uk square must be equal to u of k into k, right, and that u of k is k to the minus 5/3. So I choose the u of k accordingly. Right? That means the u for small k's will be larger than the u for large k's. And the way they decay will behave like this, k to the minus 5/3. Then I will get the right spatial structure for my flow, at least statistically. Okay, so this is why I want to talk about it in this course. And we will use later a flow field that tries to mimic this kind of Pavlov behavior, okay, for the spatial variation. Any questions on this? Okay, so now this idea was relatively simple, right? What I had introduced the last class, which is in this inertial range, you have u at scale L behaving like L to the 1/3. What I've done now is just show you implications of that in ways that can be verified, right? So one is to calculate the structure factor, the other is to do Fourier transform and get the energy spectra. You have definite predictions for the qualitative variation of both these quantities and which can be verified, right? And these have been verified in many experiments, as I said, at least approximately. Fine, so now that's okay. That's just to say that this is how we know more or less that the Kolmogorov phenomenology works reasonably well. So now what I want to do is come back to this thing and say, okay, now I have sort of said this is fine. Right? That's really the main prediction if you are above the Kolmogorov length scale. Right? And what we want to know next is what are the implications of this, right, for transport. Okay, so the first thing we look at is we have been talking about the velocity scale, velocity differences, how they vary, right, from large scales to small scales. But because I have a velocity and a certain length scale, I will have a time scale associated with that eddy. So large eddies you expect to turn slower, small eddies will maybe turn more rapidly. But how exactly will this vary? That again, in the inertial range, will have a nice Pavlov behavior. So let us see what that is. Okay, so again, we have capital T as the large time scale. Right? So we at the large time scale, we have T. In the inertial range, we will have tau L, right? And then in the dissipation range, we'll have tau eta. That controls the Kolmogorov time scale. Right? So what I want to know is look at this tau L. Okay, so I know that tau L should go like it should go like L by UL. So can you see if you can figure out what it should be? How will it scale with L? What is U? Epsilon L to the 1 by 3, right? Okay, so what this tells me now is, again, the time scale with which, again, one way to think about it as a cartoon is you have different scales, you have different eddies, some kind of gyrating motion. Right? And the larger ones have some time scale, the smaller ones spin faster. They spin faster, that means tau should be smaller. That means the time it takes for, if you watch a particle in that particular eddy, the time it takes to go around, right? It's called a turnover time. So this eddy turnover time, or the typical time scale of processes on that scale, gets smaller and smaller as L decreases. But not linearly, right? But as a power law, L to the 2 by 3. Right? So if L is small, this means the time is decaying. That means the time is bigger than if it were linear. Okay? But it's not constant. That's the important thing. It is decreasing with L. If my flow was smooth, like a laminar flow, that means if UL is proportional to L, then the L will cancel. Right? That's what will happen in the dissipation range. And tau L in dissipation range will be a constant, right? Which is just tau eta. That's why I put only tau eta there. Okay? So there is, the variation happens only in this inertial range. Right? The large scales, you have this capital T, they control the big. So for example, if there's a fan in this room, the time it takes for the fan to turn round is setting the time scale of the big eddies. At the smaller scale, you have the Kolmogorov length, the Kolmogorov velocity, that basically sets the Kolmogorov time scale. So the Kolmogorov time scale will control the dynamics below the dissipation scale. Right? It's the intermediate range that you have a whole range of time scales for the different eddies that are there in your cascade. And those vary with L. Okay? So this fact means that in the inertial range, I should be able to get a power spectra. Okay, so I just showed you the previous time we had an energy spectra. That was a spectra in Fourier modes in space, right, at different wave numbers k. But when we typically think of doing Fourier transform for a periodic signal, we're talking about the power spectra that is in time. So now if I sit in a turbulent flow at a fixed position and I record the velocity, it will keep fluctuating in time. And I can do a FFT of that and get a power spectra. Right? That means how the energy varies in time. So I can do the same thing, and I should be able to derive how that power spectra will behave, right? And that will have a power law because I can see that there are a whole range of timescales sitting in different eddies. So I sit in one position, different eddies will keep passing by my probe. And if I look at long time intervals, I will sample the differences of the big eddies. If I take small time intervals, the big eddies will hardly change. It's the small eddies that will give me the temporal response. So just by looking at the power spectra at a fixed point, I will also realize that, there are different kinds of eddies in the flow. Okay, because if I take a small time difference and I just have one big eddy, almost nothing will change. If there are fluctuations even at small time differences, it's because there are small structures there which are changing rapidly. Right? So by doing a Fourier transform in time, I'll also get the same information. Okay, the idea there is that in a turbulent flow, eddies are moving all over the place. So whether I see a still of the single time snapshot of the whole field, and I will see many different eddies by doing an energy spectra. If I just look at one point and wait for long times, all those different eddies will pass by my point because the flow is behaving randomly, right? And then I'll get the same information in time. So there should be a way to relate, and that's what I've done here, right? I've related the time scales to the velocity scaling behavior in space. So how can we do that with the spectra? Okay, so the idea is to say that I have a relationship between, if I sit at a fixed point, what is the frequency, right, with this spatial information. So I'm going to say that instead of wave number k, I have omega, which is the temporal frequency. Okay, and omega behaves like 1 by tau L. Okay, so omega at a particular scale L. Right, and so that itself. So then I can relate again L to the, right, it's epsilon to the 1 by 3 L to the minus 2 by 3, which is epsilon to the 1 by 3, k to the 2 by 3. Okay, so neglecting this epsilon factor, if I just want to look at the behavior, it goes like k to the 2 by 3. So what this means is if I'm in my temporal signal, the part of the temporal signal that is contributed by a certain structure of length L or a wave number k, right, will have this behavior. So in other words, if I have some eddy of size L, its turnover will give me fluctuations which correspond to this frequency. Right? So in other words, the omega of a certain structure of size k equal to 1 by L or L equal to 1 by k will be k to the 2/3. That's what I have said. And so then if you compose a field out of eddies of different sizes, you will probe different frequencies. Right? If I take k equal to 1, I'll get omega equal to 1. If I take equal to 5, I get a much larger omega, 5 to the 2 by 3, and then so on. So now if I think of my field as composing all these different eddies of different sizes or contributing different wave numbers in space, they will all contribute different frequencies in time. How do I get this relationship? So now you use the fact that it's basically the energy spectra as a PDF, which means I'm going to say that so this E tilde is for the power spectra in time. Okay, so you can think of this as a one-point measurement in space, but in time. Okay, and I do power spectra. And this is a single point in time. I'm doing spatial spectra. Okay, but they're the same flow, so the total kinetic energy should be the same. Right? So that's why I'm equating them. So now you can think of this just as a change of variable, right? Or the way you change a variable in a PDF, right? So in order to, I know this, right, k to the minus 5 by 3 dk, can I rewrite it like this? Okay, the answer is that yes, because I know the relation between omega and k, right? So from here I can just say d omega is equal to what will be d omega if I differentiate this relationship? Okay, minus 1 by 3. No? Correct. So therefore, dk is equal to d omega k to the 1 by 3. But if I rewrite it in terms of omega, that means omega to the half. Right? I want to rewrite dk in terms of omega. Right? So k to the 2 by 3, that means, sorry, omega to the 3 by 2 is k. Okay, so now you substitute it in there. So you start from here, right? And dk you substitute. Or you can put that also, right? K to the 1 by 3 d omega. Okay, so I just did a change of variable. You start with what you know, and I want to rewrite this as an integral in omega. So this is k to the minus 5 by 3 dk I replace by d omega, right? So k to the 1 by 3 d omega. This becomes k to the minus 4 by 3, sorry. Right? But I know from here that that is just omega to the minus 2. minus 2. Okay, so this means again that the power spectra will be such that there are more slow frequencies and less high frequencies. That's the same as saying the amount of energy content in smaller and smaller scales should decrease. Otherwise, my flow will have huge gradients. It doesn't make sense. So for any flow field to be differentiable in the end, you want the, not even differentiable, right? So that the flow doesn't blow up. The smaller scale should not have all the energy content, right? It has to smoothen out as you take smaller and smaller scales. So here the same thing in time, right? So that my temporal signal also will be in the end something differentiable if I zoom into small enough times. And that requires this to decrease and eventually cut off and become smooth. Okay. So what we have seen is that the Kolmogorov phenomenology in the inertial range, okay, which tells you that your velocity differences go like L to the 1/3, and that the Kolmogorov spectra is k to the minus 5/3. That same thing will tell you that if you stand in one place and look at the fluctuations, you will get a power spectra that goes like omega to the minus 2, provided, right, this omega must be greater than the smallest fluctuations, which come as 1 by tau eta. Correct? Sorry, the other way around. Correct? Large omega means small time scale, right? But omega should be greater than the smallest omegas, which correspond to the largest time, so 1 by t. So that is again the inertial range of things. So why did I do all this? It's because this gives me information about how the turbulent flow fluctuates in time. So to us it will look like, okay, it's some fluctuating signal. If you do a Fourier transform of this, right, you will see that, okay, in time I have a whole range of fluctuations. Right? There are some slower fluctuations. If I look at the signal on long times, I'll see some variation, because nothing is periodic, right? It's all chaotic. But there are some variations happening on large time scales, and on smaller time scales, and on smaller time scales, and so on, right, in a hierarchical fashion, such that in fact you get a power law distribution of spectral content in all those different frequencies. Okay? So you cannot just split up turbulence into some slow oscillations and some fast oscillations. They're all possible frequencies inside. But then at some small enough, large enough frequency, right, I will hit the 1 over Kolmogorov time, and then I will have the same behavior. Okay? So this means if I go to small enough time scales, the flow doesn't decorrelate. It will become almost constant. Things won't change much. So this means the flow is clearly not delta correlated in time. It's actually well correlated once the time goes below the Kolmogorov time scale. Okay, so this means that for the white noise, right, treatment of turbulence, right, we need the observation time of whatever time of interest we have, right? So whatever the time scale at which I'm interested in the flow impacting whatever transport process I'm looking at. So I'm just calling that the observation time at which I'm looking at the flow. Okay. That should of course be much greater than tau eta. It's only on those time scales that the flow will appear to be delta correlated. If I look at the flow at finer time scales, right, then it's going to be well correlated, because you will hit the Kolmogorov time. In fact, it's not only that, right, even above Kolmogorov time, I still have a whole range of frequencies. So I should say, but, right, even then you have a whole range of frequencies, right? So it's not that you just have, so if this E of omega was such that you had a high content at small omega and then it becomes 0, and then there is some content around 1 by tau eta, then you can say, okay, there are small high frequency fluctuations and there are low frequency behavior, and if I'm interested in larger time scales, I can say all that is not important. Here I have a whole range of scales. So no matter what my time of observation is, right, anywhere in the inertial range, there are correlations happening there. Right? Because there's a complete power law spectra, it's distributed. So there is no cutoff point at which I can say, okay, I have now got all this content and then the correlations are happening at a much, much smaller time. There's nothing like that. There's always correlation. Right, so the delta correlation is a serious approximation, I would say, right? Simplification. So in space, we are able to build in the full spectral structure by taking Fourier modes with a nice power law distribution of amplitudes. We can take the Kolmogorov spectra in space and then do our stochastic modeling. But typically, if we want to get some kind of analytical results, we have to assume that the stochastic function is delta correlated in time. So I take some turbulent field, the next time instant it's replaced by some completely other decorrelated field. This is a complete, very serious, big approximation, right? Because as you can see, at every point the fluctuations, there is no time scale at which I can say it's completely uncorrelated. It is correlated at all time scales. That's what this guy is telling me. Right? It's a full broad spectra. So that is a complete drastic approximation. So we will be doing that later in this course. When one does this, it's because this is what we need to do to get any kind of analytical understanding. But we should remember that we have basically replaced a flow that is correlated at all time scales by something where we are saying, okay, beyond some time scale of my choosing, I'm just saying everything decorrelates. So it's like I'm putting all this, I'm throwing away all these correlations, okay, at all the time scales smaller than this. So that's a big approximation. And therefore, the deviations we see from this sort of stochastic modeling that we'll be doing in the next few classes from real observations will be affected by this thing. Right? This can cause, that's why turbulence is not a solved problem. Otherwise, you could just model turbulence by stochastic models and derive whatever results we want. But this is very limited to what we can get some insight, but in terms of actual quantitative predictions, there are big problems and open questions because it is correlated at all scales. Then, of course, you can make the stochastic model more sophisticated and say, I will not take the delta correlated limit. I'll cook up some stochastic field which has the correct temporal correlations. Then it will, of course, improve your predictions. And there have been efforts to do such things. Okay? So if that is the case, you would want your temporal structure of your field to obey this omega to the minus 2, just like you're also obeying k to the minus 5 third. But usually in turbulence, you will see that people neglect this and they focus on the spatial structure. Okay, so we have now a basic idea of the key ingredients of Kolmogorov phenomenology. Now there are a couple of things that I'd like to discuss that directly relate to transport, okay, specifically transport of tracers, which come back to our basic opening theme of Brownian motion and so on. So the question is, how would a tracer behave if it is placed into a turbulent flow which has the Kolmogorov phenomenology? So let us start with the simple question of what happens to a single tracer that is released at some source, and we want to see how its distance from that starting point changes, right? Like the mean square displacement. Okay, so that one could call turbulent single particle dispersion, single particle for reasons of what the next problem will be. Okay, so for now, what I'm doing is I'm saying there is some origin, okay, and I release a particle here, and then I see how it evolves in time. Okay, and then at any time I'm taking this distance, and I'm going to call it x of t. Okay, so now there is a turbulent flow. This particle is just a tracer. There is no Brownian motion. It's just following the flow. Okay, but the flow field is turbulent, so the particle can go forward, backward, and so on. And because we are assuming the flow is homogeneous and isotropic, we'd expect that the mean position should be what? Right? What would be the mean x Why? It's homogeneous flow, no? What is the mean position? If I start here and I wait for some time, maybe one particle will go there. But if I do another realization, why should it go there? It will go somewhere else. So what will be the mean? Anybody? The flow is isotropic, right? That means any direction is equally likely. So if I keep repeating the experiment and I keep getting displacements in different directions, what will the mean be? 0, right? It's just like the argument for random walk. Okay, so in fact, the whole point is that if you just follow a particle in a background flow field and look at the particle only, you will see it doing something like a random walk. Right? So we'll come back to that in more detail, but the first property of the random walk it will mimic is that its mean will be 0, just because the flow is isotropic. So the fact that it is homogeneous means the starting point doesn't matter. I put this, if this whole board is a flow field, no matter where I put the initial release point, I'll get the same statistics. Okay, so the release point location does not matter. The fact that it is isotropic means it can go in any direction equally likely. Right? That itself tells me that the mean position will be at the starting point only. So because I'm defining x to be the displacement from the starting point, it just says the mean displacement is 0. Okay. What will be non-zero? The root mean square displacement, right, or the mean square displacement. So that's what we'll look at next, right? Right, what should this be? So this will not be 0, right, because if I put, now if I can think of my ensemble experiment as putting many tracers in the same flow, right? So they will all spread out in random ways, equally likely. So the average position of all of them, displacement will add up to 0. But if I look at if I take the squares of those things and add them, then they won't cancel out. Right? Then I will get the x square will give me roughly the size of the ball squared, just like in random Brownian diffusion. But the question is, how will this grow in time? Okay. So now the answer certainly depends on, so what do we know about the flow? The flow has a whole range of scales. Correct? So if I am looking at very small times, I will be sitting inside one eddy. Okay, and the flow will look laminar to me. Okay, so we'll come back to the scale dependent business in a second. But if I'm at small times, I will basically be as if I'm in a smooth flow. Okay, and x should go linearly in time. Okay, x the velocity into time. That will be my speed. Then once I go beyond the dissipation scale, beyond Kolmogorov scale, I'll start seeing a whole range of scales. Finally, at very long times, I will go beyond the big eddies in the flow. Okay, so we can work this out in more detail, but what I want to do now is just look at the long times, right? So if I look at times greater than capital T, so I'm looking at how this displacement grows at long times, much greater than the large turnover time. Okay. Or even if you like, I'm looking at this quantity at intervals that are much greater than this capital T. So then what will happen? The turbulent flow will be having these big eddies. The big eddies are completely uncorrelated with each other. They are just moving around. So then if I look at the particle across these jumps, it will look like it is taking random steps. So if it will go in one big eddy, it will go somewhere. Then at the next time, it will go into some other eddy, it will go to some other eddy. And all these eddies are uncorrelated with each other because the flow is chaotic, right? And then in the end, I will do something like a random walk motion. So this x square will grow like t, just like it does in a random walk. This is just purely based on this kind of physical argument that you think of the flow as a bunch of large eddies now, right? And all these large eddies are uncorrelated. But what would be the diffusion coefficient of this kind of effective Brownian motion? Right, so how do you think of diffusion at the molecular scale? You say that I have some velocity of motion and some mean free path, right? And their product gives me beta square per second, the diffusion coefficient. Okay, so in this argument, what should be my velocity? Right? It will be the velocity of the eddy, right? So capital U. And the mean free path, the distance I'm going before I change my motion in an uncorrelated way is capital L. Right? So it's U into L. So this is the effective diffusion coefficient, right? So if you like, this is the turbulent diffusion coefficient. So that's U into L, or same as U square Right, so this is meter square per second, and this is meter square per second square into second. Right? So that's like saying L is u by t, or u into t rather. L is u into t. Okay, so this argument was put forth by Taylor. So he's same Taylor as Taylor-Harris dispersion, okay, but that was different. That is in a laminar flow. Okay, Taylor-Harris dispersion occurs in a laminar flow because of this variation of velocity in the transverse direction and so on. That's a different problem altogether, right? Here it's happening just because of the chaotic motion of these large eddies, right, moving in uncorrelated. So effectively, each large eddy is contributing a kind of random walk step, right? So from that argument, you can expect this to happen. And this is what does happen. So if you release a tracer and you wait for very long times and look at the long time behavior, the turbulent motion will replace a kinetic gas, right? It's like each eddy is acting like a different gas molecule just moving around randomly. And you get this kind of effective diffusion behavior on large time scales. But now, of course, something different will happen if you are looking at earlier time scales, because then you will start sampling the non-trivial structure of the flow, right? This is just like saying if you look at very large scales in turbulence, it just looks like random big eddies are doing stuff. It's only when you zoom into slightly smaller distances, you see this inertial range, Kolmogorov scale, roughness of the flow, etc. Okay? So this is like the simplest case where diffusion, where the turbulence just gives you a diffusive kind of behavior. Okay? This is in fact the, if you like, engineering basis for modeling turbulence with turbulent diffusion, whether it's on mass or eddy diffusion for mass or for heat or for viscosity. Okay? And we'll kind of make this slightly more rigorous by looking at it through stochastic modeling. But this is already the heuristic basis to say that if I'm at very large time scales, right, then I'm effectively saying that each big eddy is acting on the particle in a delta correlated way because I'm looking at the times greater than capital T. And I'm throwing away all the correlations in the flow, then you get diffusion. Then we'll get the same result, right, in our stochastic modeling when we make this delta correlated assumption. The implicit thing is, again, I'm looking at large time scales. Okay? But of course, there the contradiction is usually people use that idea to derive results at lengths smaller than the capital L because you build in the Kolmogorov spectra. So that is where things are tricky. If you say, okay, I'm larger even than the largest scale, then okay, because things are uncorrelated beyond capital T. That's what I'm saying here. So this is still okay. Fine. Now we'll come to the second type of dispersion, which is Richardson's pair dispersion problem. Okay, so we are going to look something very similar now, but we want to get some sense of how this mass transport is changing across scales. Okay? So a nicer way to see that is to take two particles and see how their relative distance changes. Okay, so this is the pair dispersion problem. So I take two particles, particle A and particle B, and I monitor their distance. I'll call it xp, okay? Distance of the pair. Now again, because the flow is homogeneous, it doesn't matter where I release the two particles initially and what their relative orientation is. Okay, these things will not matter. If I'm doing an experiment, I would average out over these things across multiple pairs. But finally, I'll get a quantity for this xp of t, okay, which will evolve depending on the starting separation. And the nice thing is I can take a very small separation below the Kolmogorov length, and I can watch how things change. Okay. So what should we expect now? If my time t, okay, is less than tau eta, okay, or the distance. So let me think of it in terms of distance. That may be better. So let's assume I start xp of t is very small, below Kolmogorov, right? And provided this xp is less than eta, that means I'm sub Kolmogorov. Then what's going to happen? Well, the way to think about it is to think of the equation for xp. Right? So if I'm below Kolmogorov, I know the flow is smooth. It's like I'm locally in a laminar world. So I can write directly dxp dt is equal to the difference of velocities, va minus vb. Okay, but that itself is just going to be some constant, which is the velocity gradient multiplied by xp. this velocity gradient, of course, will be a fluctuating thing, but more or less you can see that on small time scales, if this remains constant, you will get exponential separation, right? So at small times, I will get xp going exponentially in time, okay, with a time scale that depends on the velocity gradient. So the strict way to say it is if you take many pairs very close to each other and look at them only below Kolmogorov, you will get exponential separation where lambda is a Lyapunov exponent. This comes from dynamical systems. So you imagine taking your initial thing so small so that it takes infinite time to separate. So then you can wait for a long time and see how this behavior behaves, right? Grad U will keep fluctuating, but it will give you a mean exponential behavior. And that lambda is a Lyapunov exponent. But okay, leaving aside those details, the main point is at small distances you will separate out exponentially, the way you would in some kind of extensional flow. Okay. Then if I go, so you will have this exponential separation, then you will hit distances greater than the Kolmogorov, right? But less than the large eddy. So now I'm in the inertial range. Okay, and in the inertial range, my velocity now difference is not so nicely correlated linearly, okay, because now the flow will become rough, and I cannot take the time derivative of the position, right? The distances will change. But what I can do is still look for a scaling relationship. So I can say the xp will go like some velocity difference, right? That depends on xp into t. So basically what I'm saying is that, okay, I'm not going to think of it in terms of differential equation because my flow is not smooth, but I can still look at increments of my position xp, how they're separating, and at any big jump, because my times are constrained to be big now. So I'm not writing time here, but the fact that I'm looking at distances greater than eta, it also means I'm taking time steps in the inertial range of times. Okay, so I cannot think of a differential equation anymore. Here I could make my distance and time as small as I like. That's why I wrote a differential equation. Fine, so now if I'm taking these bigger jumps, what I can still say is any change in this xp or the evolution of xp must depend on the velocity difference at that of the two particles, right? At that distance xp into the time, right? Just dimensionally. The question is now how does the velocity difference depend on the position, on the distance xp? So what is that relation? We already know it from the inertial range scaling, right? So I know that xp should go as, this itself will go as xp to the 1 by 3, correct? So that means I will have right, which means that xp square, right, the mean square displacement will go like t cube, right, or the root mean square will go like 3 by 2, right? So in this thing I will get root mean square goes like, right, or the mean square displacement will go like t cube. Okay, this is called Richardson dispersion. So, or Richardson's dispersion law, it's also called. Okay. The important thing is, see, once again, it's nice to contrast it with the laminar situation, right? So, if you were in a laminar flow, laminar flow, of course, will do this exponential thing. But if the flow was smooth, right, it's still fluctuating, so it is not going to give you this exponential behavior, let's say. But if it was smooth or what you would expect in a non-chaotic flow, this is true of any chaotic flow. Non-chaotic flow, you would expect that xp will go like, square will go like t square. So xp goes like velocity into time. Or if you think of it not in terms of a flow, I just have two particles separating at some fixed velocity, ballistic motion. That's easier to think about, right? So we just have two particles separating at some constant velocity. Xp square will go like t square. But here you see xp square goes like t cube. So you're separating faster. Right? So you're separating faster than if you take two particles and send them in opposite directions at fixed speed. Okay? So this is in some way like an explosive separation, because if you zoom out and look at the flow, you see two particles close together and they blow apart, because this t cube is separating much faster than just ballistic motion. So one way to think about it, imagine two billiard balls are coming together. They come, they hit, and they go apart. Right? That's like an impact. In a turbulent flow, you will watch two tracers come together and separate. That separation will be much faster than two balls hitting each other. So this is described as like explosive separation. Okay? And this is what's called the Richardson law. So basically, this shows you that turbulence mixes things very fast, because if you start with a clump of stuff, in the inertial range, it will spread out much faster than if you had taken the clump of material and sent them away at fixed velocity. That already that you would think is fast. And that's definitely much faster than exponential at short times. Again, right? At long times, exponential is very fast. But if you look at early time mixing, exponential means you separate very slowly when t is small. Okay, so when you're sub-Kolmogorov, your separation will be very slow. But if you start at larger scales, you start with a ball of pollutant, and the size of that ball is bigger than the Kolmogorov scale, which will be in most applications. Then the way that ball spreads will be explosive. It will be much faster than if you had a ball of particles moving away with constant velocity. It goes like t cube. And as at small times, t cube is much, much bigger than t square, and of course much bigger than exponential. Okay, so this lies at the heart of the ability of turbulence to mix things rapidly. And it's a consequence, again, of the inertial range scaling, right, or the roughness of the flow. If the flow was smooth, then this velocity difference would go like xp, and you would get t square. It's because then you would get exponential. Right? If this goal went like xp, you would get what we had there. If it's a constant, that means you just say the flow is random and uncorrelated. Right? If the velocity differences at distance xp were just some random uncorrelated velocity, then you will just get xp going like some constant into t. But that is not the case. The correlations at inertial range give you this explosive behavior. Okay. So this is a subtle thing, right? It's not just that the velocities at two positions have nothing to do with each other. Right? It is because there is some correlation, you get even faster mixing than that situation of having a constant velocity difference. Okay, and then finally we have so I should rephrase what I said. It's not that it's uncorrelated. I'm comparing it to, as I said, ballistic motion. Right? The velocity difference were constant, then you would have x square going like t square. We'll now come to the case, what if this velocity difference were completely uncorrelated? Then I would get, again, diffusive behavior. Right? So then finally at xp greater than L, right, at very large distances, I would again get diffusive behavior. I'll get two particles doing uncorrelated diffusion. So the way this guy moves and this guy moves doesn't depend on their distance. They're both just diffusing. So then their distance also will just diffuse. Okay? So I will just get going like t. Okay, so it will slow down. So where xp square was going like t cube in the inertial range, very fast separation. Once you cross the integral, the large length scale, you will then hit the diffusive motion, which is much slow. So you have these interesting regimes of separation behavior or mixing behavior. If you put a ball very, very small, you will slowly exponentially separate out. Once you hit the inertial range, you will separate out very quickly, like t cube. And then once you cross the large scale, you have no more correlations to aid your rapid separation. You will then hit a diffusive limit. And then you will just keep spreading linearly in time. The radius square, xp square, will go linearly. So that's a big jump from, big drop off from t cube. Okay. So you can imagine a small ball slowly spreading, and then it will go very fast, and then again it will slowly spread like linearly in time. Now, to actually realize this is very difficult because you need a huge range of scales. First of all, you have to be able to have a large enough inertial range to see this power law. That itself is difficult on a computer. It's very hard. It's not been done so far directly. There are some approximate ways of trying to see this, but just by putting two tracers in a flow, you need a huge simulation to be able to realize this. And then to see this after that means you need that simulation to be that much bigger, right? So it's very difficult in one simulation to see all the full range of regimes. We've not seen it yet. And that in that sense, it's still an open problem to see whether this Richardson pair dispersion exactly works out. What are the prefactors? Is there any correction to the 3/2 and so on? But in terms of qualitative picture, it works well, right? That you have this laminar exponential type behavior at very small scales, right? And because turbulence is chaotic, you can put in the Lyapunov exponent there. Then you hit this T cube like explosive separation, and then eventually you will get diffusive behavior at large length scales, large length and time scales. Okay, so with that, we've completed most of the essentials that we wanted to look at the Kolmogorov phenomenology. Now, from the next class, we'll look at stochastic modeling of turbulence, beginning with this issue about dispersion, turbulent dispersion. Okay, and what we will see is if we take a flow field, replace it with a stochastic random field, can we derive that a scalar field would see turbulence like a diffusion? Okay. And this is what we'll take up in the next class.